We are going to cover section 1.1, which focuses on the using the language of algebra. And so in terms of our learning objectives today, we have the following. We want to be able to find factors, prime factorizations, and least common multiples. We're going to be able to use variables and algebraic symbols and understand how to use them in expressions, which leads us to our third bullet point, which is being able to simplify expressions using order of operations. And then the last two will be able to evaluate an expression and then identify and combine like terms. So let's jump into it. Our first definition in this lesson today is multiple of a number. And a multiple of a number is just, we're using the variable n here, but we know that this number n is a multiple if it's the product of a counting number and n. And that may seem a little confusing. So let's take a look at some concrete examples that I've laid out below here. Any multiple of 2, for example, is 2, 4, 6, 8, 10, 12, and so on and so forth. So you're just going up by increments of 2 each time. Whereas multiples of 3, we have 3, 6, 9, 12, 15, 18, 21, 24, so on and so forth. And so any number in the world, let's say you wanted to figure out a multiple of 12, then your next term after 12, you would just add another 12 to it. 12, 24, 36. What's 36 plus 12? 48. What's 48 plus 12? 60. Okay. Another way to say that 15 is a multiple of 3 is to simply say that 15 is divisible by 3. And so all of these definitions and terminologies will really help you later on throughout this course when you're learning about finding a least common multiple, aka a least common denominator, when you're learning how to add and subtract fractions, where we have to find a least common denominator. And so having a really good grasp of multiples, divisibilities, finding factors. This is all going to help you build and strengthen your number sense so that the more complex material later on will be not easier, but more straightforward for you guys. So our next definition we have is divisible by a number. And so if a number we'll say m is a multiple of n, then we can state that m is divisible. And so we have some famous divisibility tests that you guys should definitely practice on your own if you don't already know them. The most straightforward ones, I would say, are 2, 5, and 10. We know a number is divisible by 10 if it just ends in 0. We know that it's divisible by 5 if it ends in 5 or 0. And then we know that it's divisible by 2 if it's just an even number. And what's the definition of an even number? If it ends in 0, 2, 4, 6, or 8. Now, the two that students tend to trip up on are divisibility test by 3 and divisibility test by 6. 3, the cool trick with that is if you just sum up the digits and whatever that number is, if that's divisible by 3, then you know your original starting number is also divisible by 3. And the 6 divisibility test simply states that if it's both divisible by 2 and 3, then it is divisible by 6 as well. So we'll practice these divisibility tests in this first example. So we're asked, is 5,625 divisible by 2, for instance? Well, all we have to ask ourselves is 5,625 an even or an odd number? It's odd here, so our divisibility test by 2 fails, right? We have no. What about, is it divisible by 3? Well, let's add up the digits. What's 5 plus 6 plus 2 plus 5? 5 plus 6 is 11. 2 plus 5 is 7. 11 plus 7 is 18. And you know that 3 goes into 18. But let's say 18 was too large of a number for you. You can also sum up these digits. 1 plus 8 is 9. And we know for a fact that 3 definitely goes into 9. It goes in 3 times. So what do we have? We have yes for the second one. 3 goes into 5,625 perfectly. Okay, well, what about 5 or 10? Well, with 5, does our number end in 5 or 0? Yes, it does, which means it's divisible by 5. What about 10? Does our number end in just 0? No, which means it's divisible by 5, but it's not divisible by 10. And then last but not least, we have 6. And the 6th rule is it needs to be divisible by both 3 and 2. We know it's divisible by 3, but it's actually not divisible by 2. So, because we don't have 2 checks, we only have 1, we have no, it's not divisible by 6. Right? Some more definitions on this page. And this statement that I have above here we'll talk about in a moment, but let's just touch upon factors, prime numbers, and composite numbers first. So, definition of a factor. I like to think about factor pairs, what 2 numbers multiplied together will give you another number. But more formally, we have in the expression, we'll generalize this, A times B. Both A and B are called factors. Again, we're taking products here. So if we have A times B is equal to M, and both A and B are integers, then A and B are factors of M, right? We can do a quick example. What are factors of, we have 1 times what gives you 10? 1 and 10. Does 2 go into 10 perfectly? It does. It goes in 5 times. And these are our only factors, 1, 2, 5, and 10. Prime number. Definition of a prime number is simply if the only factors of that number contain 1 and itself. So every single prime number in the world has only 2 factors, the number 1 and then the number we're actually talking about. Formal definition, a prime number is a counting number greater than 1 whose only factors are 1 and the number itself. Why does the number have to be greater than 1? Well, what are factors of the number 1? It only has 1 factor. Therefore, the number 1 is not prime as its own special category is unique. And then we can jump up to this comment that will be mentioned on a later slide as well. But the number 2 Factors of 2 are simply 1 and 2. And fun fact, 2 is our only even number that is prime. And then our last definition on this page is composite number. So composite numbers are numbers that contain more than 2 factors. And so a good example of this, 10 is a composite number, right? Contains 1, 2, 5, and 10 as factors, but 4 also. And why? Because what are our factors of 4? Well, we have 1 and 4, and we have 2 and 2. Those are our factor pairs. So 1, 2, and 4 are all of our factors of 4. We have 3 factors here. It's more than 2. It's composite. Formal definition, a composite number is a counting number greater than 1 that is not prime. Composite number has factors other than 1 and the number itself. So the slide on this next page sort of goes through a lot of our younger numbers all the way up to 20, really going through in detail what the specific factors are, but then also defining whether this number is prime or composite. So notice how all of the prime numbers have exactly 2 factors, all of the composite have more than 2. And then I once again put that famous fact at the top, stating that 2 is the only prime number in the entire universe that is even. All other prime numbers are odd. And why is that? Well, every multiple of 2 after the number 2 itself will contain that factor of 2 in addition to 1 in itself, and then maybe even other numbers. Right? Another notes page, we have a composite number can be written as a unique product of primes, and this is known as prime factorization. So our more formal definition of prime factorization is taking the product of prime numbers that equals the number that we started with. And these are known as prime factors, the prime numbers that we're dealing with. So below here is the step-by-step procedure in order to find the prime factorization of a composite number, but we'll practice over the next slide, taking it in a more concrete manner. So we're asked to find the prime factorization of 48. I'll write 48 again here, and I like to use the factor tree method. Which essentially goes through factors of 48 and then us circling the prime numbers within our tree. So we first want to ask ourselves, what 2 numbers multiplied together give you 48? Any 2 numbers in the world besides 1, because that won't really get us anywhere. So let's start with, we know it's an even number, so 2 has to go in. 2 goes into 48 24 times. And then we ask ourselves, is 2 prime? Ooh, it is. If it's prime, we circle it, and we're done with that branch extension, hence factor trees. Then we ask ourselves, okay, is 24 prime? It's not. It's composite. It can be broken up into 2 and 12. So we created some more branch extensions. Ask yourself again, is 2 prime? It is indeed. Circle it. We're done with that side. Is 12 prime? It is not. Let's break this up. We can break it up into 2 and 6. Is 2 prime? It is. We'll circle that. Is 6 prime? It's not. That can be broken up into 2 and 3. Is 2 prime? Once again, it is. Is 3 prime? It is. We have all of our circles. So we are completely done. We can rewrite 48 as 2 times 2 times 2 times 2, taking all those circled numbers, times 3. But as we learned earlier, or I guess we haven't learned earlier, as you've learned in your previous math class about expanding an exponential form, we can rewrite this 2 times 2 times 2 times 2 as simply 2 to the fourth. And so this is our prime factorization form, fully simplified. We're done. These are all of our prime factors of 48. Right, we have another notes page. So one of the reasons we look at primes is to use these techniques to find the least common multiple of two numbers. And this is going to be very useful when we're learning how to, once again, add and subtract fractions with different denominators, when we have to find that least common denominator. Least common multiple is just another way of stating our least common denominator. And so our formal definition of least common multiple, aka LCD, is the least common multiple of two numbers is the smallest number that is a multiple of both numbers. And so this is just the step-by-step procedure in finding the LCM using our prime factors method. Right, so let's go to the next page where we have some more definitions. We have the formal definition of a variable, which is a letter that represents a number whose value may change. We can also just call it an arbitrary value, a value that can be, for example, 1 or 5 or -2. And then we also have a constant, and a constant is a number whose value always stays the same. So if you see like a +4 in an expression or an equation, that's known as a constant. And then down below here, we just have our 4 operations: addition, subtraction, multiplication, and division. And so in terms of notation, addition and subtraction only have one, but there are multiple ways to represent multiplication, and there's a few ways to represent division as well. The more notes we have when two quantities have the same value, we can connect the two with an equal sign. So for example, A equals B. And then we have our inequality symbols. This first inequality stands for less than. I like to read it from left to right when it's pointed on the left. Then we're looking at the smaller number on that left-hand side. And when it's nice and wide as like a big mouth, like an alligator mouth, it's eating that larger number. So this stands for greater than. All right. This is our inequality symbols in a little bit more detail. Now we're looking at inequalities that have a line underneath, which include the value. So this just stands for A is less than or equal to, whereas this one over here stands for A is greater than or equal to. And then the one thing we didn't touch upon yet is what if there's a slash over that equal sign? That just stands for is not equal. This slide is just talking about how to properly notate groupings in mathematics. So we have our basic groupings of parentheses, but let's say we wanted to group parentheses, we would put them in brackets. And let's say we wanted to group brackets, we would put them in what's known as braces. Parentheses and brackets have other meanings in math that we'll learn about later on throughout this course. dealing with interval notation and inclusivity and exclusivity. But for the time being, let's just view these as ways to group expressions in math. And I did like a small little example here. We're grouping some parentheses through brackets, and we're grouping a bunch of brackets through braces. And so on this slide, we have, once again, a few more definitions. We have an expression, which is a number, of variable, or just a combination of numbers and variables. I have some examples here. Up here are some examples of expressions that include those groupings that we spoke about on that previous page. And then last but not least, on this page, we also have what's known as an equation, which is simply two expressions connected by an equal sign. And I have some examples down here. Also, an equation does not have to be just two expressions. It could be multiple expressions. This is our formal slide of exponential notation that I sort of very lightly touched upon in one of our first examples today. And so if we're looking at 2 times 2 times 2, and there's 9 2's here, it can be quite tedious to keep track of all these 2's. And so we wanted to come up with a better system that we call exponential notation, where we can simplify this to just 2 to the 9th power. There's 9 2's. And so that exponent represents how many 2's are being repeated. And so down here, that's what we're formally talking about. How do we convert exponential into standard form or expanded notation and vice versa? Being able to simplify an expression, what you want to utilize is what's known as our acronym PEMDAS. Each one stands for a certain procedure to do. So parentheses first, then your exponents. And then multiplication and division are on the same level, but whichever one comes first in your expression or your equation, that's the one that you're doing first. And then the same goes with addition and subtraction. Whichever one comes first as you're reading your problem from left to right, that's the one you're going to facilitate and simplify first. And the details of what each of these letters, again, stand for are on this page. The acronym we like to use is our whole "Please excuse my dear Aunt Sally," so that you remember the order properly. All right, so let's jump into example 4 and give this a shot. We are going to utilize our PEMDAS. Let's take care of our parentheses first. Minus 2 gives us 3. And I'm going to rewrite the problem. And then we want to do our division first because we're reading the problem left to right. 18 divided by 6 gives you 3. Rewrite the problem. Now 4 times 3 gives you 12. Rewrite the problem. And then finally, 3 plus 12 gives us our final simplified result, which is 15. Let's take a look at another example together. Once again, parentheses first. 4 minus 2 is 2. Rewrite the problem. Some exponents, 2 to the 3rd is 8. Simplify that. Let's continue with our parentheses. So we have 3 times 2 gives you 6. And rewrite the problem. Six minus 6 gives you 0. Rewrite the problem. Keep rewriting the problem until you're very comfortable with doing these types of problems. 3 times 0 is 0. Rewrite the problem. And then read it from left to right. 5 plus 8 gives you 13, plus 0 gives you 13. And so this is our final result. Right, another definition here. Evaluating an expression. So to evaluate an expression is just another way of saying to find the value of the expression when the variable is replaced by a certain number. And so in example 6, we want to evaluate each expression below when x is equal to 4. So wherever you see an x, you're going to first draw some parentheses and finish up the problem. We're not filling the parentheses in quite yet. And now, inside those parentheses, you are going to insert your value of x, which is 4. And then you simplify using your order of operations. 4 squared, very straightforward. We get 16 for that first one. 3 times 4, another straightforward example, you just get 12. And then the last one, we have 4 squared, which gives us 16. We have a 3 times 4, which gives us 12. 2 times 16 gives you 32. And then 32 plus 12 plus 8 is the same as 32 plus 20, which gives you 52. And we're done. Identify and combining like terms. So once again, we have another definition. A term is a constant or the product of a constant and one or more variables. And so these are some examples of terms: 7y, 5x squared, 9a, b to the 5th. If I wrote this expression out, 3x minus 5y plus 20, the terms are separated by minus or plus signs. So we have 3x is one term, we have negative 5y is another term, and we have a positive 20 is another term. Coefficient. Use a different color, let's use purple. The coefficient of a term is the constant that multiplies the variable in a term. So if we're looking at 3x, the coefficient of 3x is the number in front, it's 3. If we were looking to simplify the expression 3x plus 4x, combine like terms, because these have the same variables and same exponent. So we just look at the coefficient, add those numbers together, 3 plus 4 is 7, and then stick that same variable on the end. And so that brings us to the formal definition of like terms, which are terms that are either constants or have the same variables raised to the same powers, which is what we have here as that example I just spoke about. So let's apply this to our example 7. We have our sort of step-by-step procedure up here, formally talking about how to properly combine like terms. But with example 7, I'm going to color code 2x squared is a like term to x squared. We have 3x is a like term to 4x. And then we have our two constants, which can be completely different numbers, but we can always add numbers to one another. So those are also like terms. So add the coefficients and keep the same variable at the end. 2x squared plus x squared is the same as 2x squared plus 1x squared, and 2 plus 1 gives you 3. So we have 3x squared. 3x plus 4x, well, 3 plus 4 is 7. Keep the same variable, we have x. And then finally, 7 plus 5 gives us 12, so we have a plus 12. And so simplified form is 3x squared plus 7x plus 12, and we're done. And so this concludes our section 1.1. Next time, we will be learning about our section 1.2. I hope this was helpful. Let me know if you guys have any questions. Okay, take care. Bye.